Imagine standing in the absolute heart of Death Valley. The air is so dry it feels like it is cracking your skin. The sun is beating down with a relentless, punishing ferocity. In a place like this, water is usually a distant memory, pumped from deep underground aquifers or piped in from hundreds of miles away. But right now, in the middle of this scorching landscape, a device that looks like a piece of geometric modern art is performing what looks like a miracle. It is not connected to a pipe. It is not plugged into the grid. It is sitting there, silently, pulling fresh, drinkable water directly out of the thin, burning air. This isn't science fiction. This is the dawn of a new era in atmospheric water harvesting, led by a groundbreaking innovation known as Hydrogel Origami. Today, on G Fun Facts Online, we are doing a deep dive into the technology that is turning the sky into an ocean. You might not realize it, but right now, above your head, there is a massive, invisible river. The Earth's atmosphere holds an estimated 12.9 trillion tons of fresh water. That is 6 times more water than all the rivers on Earth combined. For decades, this massive reservoir has been tantalizingly out of reach for the people who need it most. We have known how to harvest water from the air for a long time, but traditional methods have a fatal flaw. They rely on condensation. Think of a cold can of soda on a hot day. Water droplets form on the outside. That is condensation. We have massive fog catchers and dew condensers that work on this principle. But here is the catch. They need humidity. Fog catchers need 100% humidity. Condensers, like the one in your air conditioning unit, become energy vampires when the humidity drops below 50%. In the desert, where the relative humidity often drops below 20%, these machines are useless. To get water in the desert, you do not need a cold surface. You need a molecular sponge. You need a material that actively hunts down and traps water molecules even when they are incredibly scarce. This is the domain of sorption-based harvesting, and that is where the breakthrough happens. At the core of this revolution is the hydrogel. You have actually seen simple hydrogels before. They are in baby diapers and potting soil. They are 3D networks of polymers that love water and swell up when they get wet. But a standard hydrogel isn't enough for the desert. Scientists needed a material that could suck water from bone-dry air, hold it tight so it doesn't evaporate immediately, and then release it easily when we want it to. The secret sauce to making this happen is salt, specifically lithium chloride. Lithium chloride is a chemical champion of water grabbing. It is so hygroscopic, which means water-loving, that if you leave a pile of it on a table, it will pull so much moisture from the air that it eventually dissolves into a puddle of its own making. Researchers at MIT, led by Professor Xuanhe Zhao and Dr. Chang Liu, had a brilliant idea. They decided to infuse hydrogels with this super thirsty salt. They used a polymer called polyvinyl alcohol, or PVA, as the structural backbone. The idea was to let the salt pull the water in, while the polymer chains held the salt in place, creating a stable, swellable solid that does not leak. But creating the material was only half the battle. The second challenge was speed. And this is where the engineering gets really clever. Imagine a thick block of this hydrogel. It absorbs water, but it does it slowly, because only the outer layer is touching the air. In a desert, the window of time to collect water is short, usually just the cool hours of the night. A thick block simply would not absorb enough water fast enough to be useful. You need surface area. Lots of it. This is where the concept of origami changed the game. In a landmark study published in Nature Water in 2025, the MIT researchers unveiled a device that utilized an origami-inspired design resembling high-tech bubble wrap. Instead of a flat sheet, the hydrogel was molded into an array of small, hollow domes. This wasn't just for aesthetics. This shape creates channels between the domes that allow air to flow freely around the entire surface. It doubled the effective surface area, allowing the material to breathe. It also gave the material structural stability, so it could swell and shrink without buckling or tearing. So how does this actually work in a real-world scenario? The beauty of the hydrogel origami system is its passivity. There are no pumps, no fans, and no batteries. It breathes with the rhythm of the day. The cycle begins at night. As the sun sets over the desert, the temperature drops and the relative humidity rises slightly. The box containing the hydrogel panels opens up. The cool night air flows over those origami domes. The lithium chloride ions inside the gel start grabbing water molecules from the air. The hydrogel swells, storing the water safely inside its polymer network. It is effectively charging up with water. Then comes phase 2, the day. The sun rises and the ambient temperature soars. The device is enclosed in a glass case, basically a solar still. The black hydrogel absorbs the sunlight and heats up. This heat breaks the weak chemical bonds holding the water molecules. The water evaporates out of the gel, turning into hot vapor inside the glass case. That vapor hits the relatively cooler glass walls, condenses into liquid droplets, and slides down gravity-fed channels into a collection reservoir. The result is pure, distilled drinking water, harvested from thin air, powered by nothing but sunlight. But does it actually work outside the lab? To prove this wasn't just a curiosity, the researchers took their device to the ultimate proving ground, Death Valley, California. The conditions were brutal. Daytime temperatures were scorching, and relative humidity was as low as 21%. Despite this, the meter-scale device produced up to 161.5 milliliters of water per square meter per day. Now, 160 milliliters might sound small, like half a soda can, but in the context of physics, it is a triumph. It proves that scaling this up to just a few square meters, roughly the size of a solar panel array, could provide the 3 to 4 liters of survival water needed for an adult daily, entirely off-grid. And importantly, the water was pristine. The specialized polymer network successfully kept the toxic lithium ions trapped inside the gel. The lithium concentration in the drinking water was less than 0.06 parts per million, which is far below the safety limit. You might be wondering, are there other technologies that do this? Yes, there are, but Hydrogel Origami has a massive advantage. Its main competitor is something called metal organic frameworks, or MOFs. MOFs are like the Ferrari of sorbents. They are highly engineered porous crystals that are incredible at trapping water even at 10% humidity. But like a Ferrari, they are expensive. They often require exotic metals like zirconium and are complex to manufacture. Hydrogels, on the other hand, are the Toyota of the industry. They use cheap, abundant materials like PVA, salt, and cellulose. They are reliable, affordable, and scalable. The MIT study is just the tip of the iceberg. Other institutions are joining the hydrogel revolution. For example, a team at UT Austin has developed a super sponge using bio-derived hydrogels made from konjac gum and chitosan from shellfish. These are biodegradable and sustainable. They have even developed microgels that release water at lower temperatures, making the solar heating phase even more efficient. One of the most exciting applications isn't just drinking water, but agriculture. Researchers are experimenting with mixing these hydrogels directly into the soil. Imagine a farm in a region where it never rains. At night, the soil itself absorbs moisture from the air. During the day, as the soil heats up, it releases that water directly to the plant roots. This could create a self-sustaining irrigation cycle powered entirely by the atmosphere. But let's talk economics. Is this affordable for the people who really need it? The numbers are promising. The estimated material cost for the MIT device to supply daily water for one adult is approximately $3.20. The levelized cost of water is estimated between 5 and 10 cents per liter. While that is more expensive than tap water, it is vastly cheaper than bottled water, and competitively priced for remote communities where the alternative is trucking in water at huge expense. As manufacturing scales up, imagine roll-to-roll printing of these hydrogel sheets like newspapers. Those costs will plummet even further. The future applications of this technology extend far beyond a box in the desert. Architects are imagining skyscrapers with skins made of hydrogel panels. As the building releases harvested water, the evaporation process would cool the structure, slashing air conditioning costs while simultaneously harvesting gray water. In emergency response scenarios, where floodwaters are everywhere but clean water is scarce, lightweight, foldable hydrogel sheets could be airdropped to survivors. You unfold them, leave them overnight, and by noon you have sterile water. We are standing on the precipice of a blue revolution. Just as solar panels decentralized energy, allowing anyone with a roof to generate power, Hydrogel Origami has the potential to decentralize water. It democratizes access to life's most essential resource. No longer bound by proximity to a river or the utility grid, communities can thrive in the arid lands that cover 40% of our planet. The technology is proven. The materials are cheap. The geometry is perfected. The sky is no longer empty space. It is a vast, floating ocean. And thanks to the folds of a simple hydrogel sheet, we finally know how to drink from it.